Hello everyone, and welcome to my channel. This is a channel for educational purposes. We try to shed light on some great theories of everything that I've come across in my research and to do some deep diving into so that you can see the possibilities. And today is our 447th video on the reciprocal system of theory from Dewey B. Larson. Dewey B. Larson was an American engineer who lived in the 20th century, died in 1990. Around 1959, he put out his two fundamental postulates about how he believed the universe operated. And then shortly thereafter, he began to, or even maybe before, he started to elaborate on those two postulates through a process of deduction. If my postulates are correct, what would my universe look like? And so he defined his theoretical universe. And then in some of his volumes, he compared his universe to the measured universe of the scientists, especially that what they have measured in their laboratories and compiled in their scientific tables. Also, in their, what do you call them, observatories, and in their astronomical tables. I don't mention this often as I should, but in 1959, that same year, Larson predicted the existence of quasars in several details about what they were. And that was like 3 years before quasars were discovered. So his track record is formidable. He was able to predict the existence of things that had not even been discovered yet. And so that also, gives him more credibility in terms of that maybe his theoretical universe is worth considering. It doesn't mean it's right, but it's prima facie evidence. And then we're looking at his book on chemistry here called Basic Properties of Matter. Larson calculates, first he derives equations for many of the basic properties of matter, such as the compressibility and the interatomic distance and the melting point. And then he compares them with the tables and compares them very favorably. So either Larson is like fudging the numbers or he is onto something, in my opinion. And so that's why we're taking a look at his work here. We're looking at chapter 5 in this book, Basic Properties of Matter, which is on heat. And but before we get to that, we'll try to give you a little once-over on what the reciprocal system of theory actually says. First, it's a system of theory, meaning that it is an interconnected series of theories. So there's a theory for astronomy, there's a theory for chemistry, there's a theory for physics, there's a theory for economics, there's a theory for religion, metaphysics, philosophy, all these things, and they're all interconnected. They all are based on the same principles, and in many cases you can use the same equations across fields, which is so much different than the pigeonholed, jargon-laden curriculum of modern, Western life, where, you have to go to graduate school and study for 7 years to learn, biology, but then you don't know jack about any other subjects because what you've learned about biology doesn't apply to anything else. But here, if you learn something in one field, it will apply to other fields as well. It's an interrelated, a system of theory. And then the reciprocal system is also known as the universe of motion, because Larson attempts to build his universe upon motion. His first postulate reads as the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, so we've got motion, we've got 3 dimensions, we've got discrete units, and we have 2 reciprocal aspects, space and time. Okay, when Larson's talking about motion, he's talking about something more generalized that is called a scalar motion. A scalar motion is a motion that has a magnitude, but it has no specific direction. You can envision a scalar motion with a balloon that you put dots on. If you blow up the balloon, all of the dots will be moving away from each other. They won't be moving in any specific direction. They'll, in fact, be moving in all directions. Every dot will be moving away from every other dot. And really every point, every location on the surface of that balloon will be moving away from every other location on that surface. So it's a motion in all directions, therefore no specific direction. And really the directions are just in or out, depending on whether the balloon is expanding or contracting. The expanding balloon Larson calls the progression. The contracting balloon he refers to as gravitation. And this basic motion can occur really in 3 dimensions. And you can also abstract this motion if you decide that you want to assign a reference point to one of the dots. You say, this dot, for the purposes of my, sanity here, is motionless. And then you can start to measure the directions, and you will be able to see that all of the other dots will be moving either toward or away from that other dot. And it will look as if there's a force field. It will look as if there's an attractive force or a repulsive force emanating from your reference dot, and that it is affecting these other dots. But in fact, all of the dots are actually just following their own path. They're all moving toward each other. And so there is no force. Larson refers to this as an as-if force. It looks like there's a force, but there isn't. And it actually mathematically computes to a force. There is an inverse square law of the gravitational force, and the dots will comply with that inverse square law, but there isn't any force. It's each one of the dots is pursuing its own course. Now, if you take that idea of this assigning a reference system and basically stopping the universe or abstracting, the whole moving motion universe, then you get the spatial reference system and the temporal reference system. So the spatial reference system is what we're familiar with here in the, in our environment here in the universe, where we perceive 3 dimensions of space in a still frame, coordinate space, X, Y, Z coordinates. And it appears to be like a background that we're moving through. And so we see this coordinate space along with clock time. So the clock time is a scalar motion in time. Time is getting later and later and later, and it's not moving in any specific direction. Now, if we were in a different environment of the universe, we would perceive the inverse of that, which would be 3 dimensions of time in a still frame, and progressing space. Space would always be getting later and later and later, like in a scalar manner, like on the surface of an expanding balloon. But time would appear to be motionless, and you could measure it in three dimensions with vectors. So that's, vectorial motion in space or time in their spatial or temporal reference system. Now, it's important to keep in mind that in order to describe these three dimensions of space or time, you only need one dimension of motion. Okay, so you have three dimensions of motion, but you only need one to describe the spatial reference system, and you need one to describe the temporal reference system. Okay, now you also have this reciprocal relationship between space and time. This seems a little bit absurd. The reciprocal of space is time, but if you just look at our most basic motion, speed, the car is moving 15 miles per hour. That's 15 miles of space in 1 hour of time, space over time. And if you double the speed, then you would say the car is moving 30 miles an hour now. Or, equivalently, you could say the car is now moving 15 miles per half hour. So you can double the space, or you could halve the time. That is a reciprocal relationship. And so there is a reciprocal relationship in speed, at least. Larson spreads that out and applies it to all scientific phenomena. He equates all scientific phenomena to motions. So in Larson's world, matter is a kind of motion. Energy is a kind of motion. Temperature and pressure are kinds of motion. Electrical charge is a kind of motion, and so on. So, and he says that they all are reciprocal relationships between space and time. Basically, all of our scientific quantities are fractions, with space or time as the numerator and time or space as the denominator, keeping in mind that time and space can be multidimensional. Okay, and then we have the discrete unit postulate. Now, first, in order to really even get with the concept of a universe of motion, you have to be able to understand that motion exists before anything moving. You have an empty universe where motion is the only thing existing. You have motion of nothing. And in fact, the thing that would be moving is motion itself, because matter is a form of motion. So Larson has what he calls the null point or the neutral point, the 0 point. He calls it the progression of the natural reference system. And this is the progression, like on the surface of that balloon. It's always progressing 1 unit of space per 1 unit of time. And it turns out that 1 unit of space in 1 unit of time is the speed of light. So Larson refers to that as unit speed, or the speed of light. So that is the null point, or the 0 point, or the ether, the origin, the source of this universe is motion outward at the speed of light in all directions. And he refers to that as the progression of the natural reference system. So as the midpoint, or the null point, you get half of the universe is actually moving slower than the speed of light, and half is moving faster than the speed of light. The half that's moving slower is called the material sector. The half that's moving faster is called the cosmic sector. In the material sector, you have coordinate space and clock time. In the cosmic sector, you have coordinate time and clock space. And so that shows not only the reciprocal relationship between the two sectors, but also that when you cross that boundary, the rules reverse and the roles of space and time are interchanged. Now, within both the material sector and the cosmic sector, you have an inside region that also has to do with the discrete unit postulate. The discrete unit postulate is basically that space, time, and motion come only in discrete units. You can't have half a unit or 0.23 of a unit. You either have a whole unit or you don't have anything. And so in the material sector, you have atoms and molecules that are interacting in less than 1 unit of space. 1 unit of space is approximately 2 millionths of an inch. It's very large compared to the size of atoms. And so when atoms interact in this small space, they don't interact in space because there isn't space, because it's less than 1 unit of space. And if you don't have a full unit of space, you don't have space. So if you don't have space, you only have time, because the universe is made out of space, time, or motion. And so it's got to be one or the other or both. So if it's not space, it has to be time. Larson refers to this as the time region. And in the time region, again, when you cross that border into the time region, the rules reverse. And now the progression is moving inward. The progression of that formerly expanding balloon is now moving inward, but really it's still moving outward in time. But we see it as moving inward in space, because space and time are reciprocals of each other. And the gravitation is now moving away. So the progression is causing pressure or compression, and gravitation is causing repulsion, or I suppose you could say, spreading out or moving farther apart. And there is a spot where those two forces are equal, because the progression is constant. It's omnipresent, eternal, and it's always the same. It's 1 unit of space per 1 unit of time. But gravitation is variable based on this inverse square law. And so there is a point where they are the same. That's called the equilibrium distance. And Larson refers to that as the interatomic distance. This is the distance between atoms that are packed together in the solid state. So the same thing also happens in the cosmic sector, except that happens with cosmic atoms and cosmic molecules, what we call antimatter. And it occurs in what Larson calls the space region, because it occurs in less than 1 unit of time. But again, the rules reverse, and the progression is now inward and gravitation is now outward. Now, an atom is formed based on the progression, which is the source, and it's based on reversing the progression in 3 dimensions. You first reverse it with a photon, which is a vibrating unit, and then you reverse the photon with rotations, 2 two-dimensional rotations and 1 optional 1-dimensional rotation in the opposite direction. And that is those are the numbers Larson uses for his periodic table. It's a 3-number system, 3 motions. The primary 2-dimensional rotation, a secondary 2-dimensional rotation that alternates with the first, and then a 1-dimensional rotation in the opposite direction that can be 0 in the noble gases, and it can be positive or negative. And so these are kind of the basic factors Larson's dealing with when he deals with the basic properties of matter, as in this book here. Now, in chapter 5, we got to a point where we were talking about the specific heat curve. Heat is really, it's a disruptive force to the atom. So, once you get to your equilibrium position, then you deal with forces of compression, which will tend to force that equilibrium position even closer together, and the forces of heat, which are going to move that equilibrium position farther apart. And Larson discussed the various aspects of heat that move it apart and that cause it to eventually leave the time region entirely, which is in one dimension. When it leaves the time region, it is called the melting point. And when it leaves the time region in all three dimensions, it's referred to as the boiling point, or becomes a gas. There's also a heat increment that you have to get to kind of cross that border, the heat of fusion or the heat of vaporization. But there are various expedients that the atom can use in order to kind of stave off leaving the time region, because it wants to stay in the time region. And one thing that it can do is it can, to modify the specific heat curve, is it can kind of change the well, let's let Larson explain it here. Okay. When the rotation 2 curve reaches its endpoint at 2.917, okay, before that, he calculated here the specific heat, which is the amount of heat that you need to add to accomplish a certain temperature change in a certain element. And that specific heat pattern, also, it has units, just like everything in Larson's system has units, like, because it's a discrete unit system. And basically, he found that using the gas constant, which is a measure of the specific heat. And when the gas constant gets up to 2 1/3 units, when it gets to 3 units, it leaves the time region in one dimension. But because of the photon and the vibratory nature of the photon can add 2/3 or subtract 2/3 from that number. And so so when it's subtracting 2/3 of that number, the number needs to be 2 1/3. But before it gets to 2 1/3, the second rotational unit is activated. And when you use the second rotational unit, because it's a 3-dimensional distribution, you have to divide by 8, 2 to the 3rd power. And so now, like he says, the pattern is followed up to the 2 1/3 level. At that point, the second rotational unit is activated. The initial specific heat level for rotation 2 is subject to the same n to the 3rd factor as the thermal specific heat, and is therefore 1/12 instead of 2/3. And this change in the negative initial level raises the net positive specific heat corresponding to the thermal value 3R up to 2 11/12, as opposed to 2 1/3. And enables the thermal motion to continue on the basis of the preferred negative initial value. And this causes the specific heat curve to bend. And then when it gets up to 2 11/12, it can change again to the rotation 3 basis, which is based on 3 to the 3rd power, and which is 27, and 1/2 of that, or 2/3 of that, is 2/81 which is approximately 2.975. Okay, that was the number. I couldn't figure out where he got that from, but it's because I was forgetting to divide by 2/3 there. So when the rotation 2 curve reaches its endpoint at 2.917 R. R is the gas constant. Our net positive specific heat, a further reduction of the initial level by a transition to the rotation 3 basis, where the higher rotation is available, raises the maximum value to 2.975, or 2 in 79/81. Another similar transition follows if a fourth vibrating unit is possible. The following tabulation shows the specific heat values corresponding to the initial and final levels of each curve. As indicated earlier, the units applicable to the second column under each heading are calories per gram mole per degree Kelvin. So he has a table here, and he's showing you the negative specific heat level. Once you get up to that 4 level, you're dealing with really 1 out of 96, because 4 to the 3rd power is 64, and you take 2/3 of that. So 1/64 times 2/3 is 2 over 192, 1 over 96. And so that level goes all the way up to 2.9896, and that takes the specific heat level up even higher. Ultimately, the maximum net positive specific heat that is possible on the basis of a negative initial level is attained. Here, the transition to a positive initial level takes place, and the curve continues onto the overall maximum, which is 3 2/3. So now the whole photon, what does he say? Transition to a positive initial level. So it switches from the negative initial level to the positive initial level of the original photon that's at the core of every atom. And so now you get to go all the way up to 3 2/3, whereas before you were just up to 2.9896. So the atom naturally does everything that it possibly can to avoid crossing this boundary. First it goes to rotation 2, then rotation 3, and maybe rotation 4, and then it flips over to the positive initial level. And the curve continues on to the overall maximum. As a result of this mechanism of successive transitions, each number of vibrating units has its own characteristic specific heat curve. The curve for rotation 1 has already been presented. And so the curve for rotation 1 is just a straight curve. And then the curve for rotation 2 has one shift. Well, the curve for rotation 1 is really a straight curve till it gets to the point where it shifts to the positive initial level of the photon, and then it goes up. The 2-level curve shifts twice, and then the 3-level curve shifts 3 times, and the 4-level curve shifts 4 times. For convenience, we will call this a type 2 curve. The curve for rotation 1 has already been presented. He calls it a type 2 curve, just to make it more confusing. And then the different type 1 curves, those of 2, 3, and 4 vibrating units, are shown in figure 4. As can be seen from these diagrams, there is a gradual flattening and an increase in the ratio of temperature to specific heat as the number of vibratory units increases. The actual temperature scale of the curve applicable to any particular element or compound depends on the thermal characteristics of the substance. but the relative temperature scale is determined by the factors already considered. And the curves of figure 4 have been drawn on this relative basis. So depending on what kind of an atom you have, it's going to take one of those different kinds of curves. As indicated in the equation, which is 2t over n to the third. So 2 times temperature over the n to the third, the number of rotations. The slope of the rotation 2 segment of the specific heat curve is only 1/8 of the slope of the rotation 1 segment, while this second segment starts at a temperature corresponding to 2 1/3 specific heat, rather than from 0 temperature. The fixed relation between the two slopes means that a projection of the 2-unit curve back to 0 temperature always intersects the 0 temperature ordinate at the same point, regardless of the actual temperature scale of the curve. So he's taking these line segments from the inflection points of the curve, and he's projecting them back all the way to the 0 point, the 0 temperature ordinate point at the same point. And so regardless of the temperature scale, the line projects back to the same point on that vertical axis there. The slopes of the 3-unit and 4-unit curves are likewise specifically related to those of the earlier curves, and each of these higher curves also has a fixed initial point. We will find this feature very convenient in analyzing complex specific heat curves, as each experimental curve can be broken down into a succession of straight lines intersecting the 0 ordinate at these fixed points, the numerical values of which are as follows. And so the first curve intersects at minus 0.132, the second one at 3.89, this third one at 5.23, and the fourth one at 5.62. Okay, I think that's about it here for today. And, you know, don't feel like you're getting lost here. This is all in the weeds, and it's all like more advanced than you probably need for learning being a beginner in the reciprocal system. But I'm just trying to quote Larson because I'm not able to express what he's saying fully. And I want to put it on the record so that a person, if they really are studious, they can get it. And hopefully I will clarify these as I learn to understand them. All right, thanks for tuning in.